This PowerPoint is over forces in 2 dimensions. So here we're going to talk about free body diagrams in 2 dimensions. In the following examples, what does the free body diagram look like for each scenario? So for the first one, we have a guy who is walking a dog. Now the prompt says that a dog being walked. So we're talking specifically about the dog that's being walked. So we're making the dog our system. That's what we're looking at when we look at the forces that are applying to our system. Now if you notice on the dog, there are several forces. You got the force of gravity, obviously, with a gravitational field. You also have the normal force that's pushing upward, and then you have the force of tension. Now notice the force of tension is actually along the line of the guy who's holding the leash. So that's the direction of the force. It's going to be up at an angle. It's not going to be horizontal. It's going to be at an angle. And then if you look at force of friction is actually going to be forward. Now if you think about this, think about the dog that's pushing on the ground. Now the dog's pushing on the ground back, but the ground is pushing on the dog forward. And since we're looking at the dog as our system, then really we're just looking at the forward force due to friction. So we make the dog again our system. That's going to represent the dot, and then we have all of our forces that are acting on our system. And this is what our free body diagram will look like for the dog being our system. The next example is going to be a car that's on an incline. So referring to a stationary car in an incline, so it's not moving, not sliding, nothing weird going on here. So if we look at the forces, of course we're going to have the force of gravity pulling down on it, but we also have normal force. Now normal force, the term normal actually means perpendicular. So the normal force is going to be perpendicular to the surface itself, and since the surface is inclined, and that means the normal force is not going to be straight up, it's actually going to be perpendicular, which is now going to be at an angle. And since the car wants to slide down, but it's not, the ground is pushing up on the car, and that's causing the force of friction to be up the ramp. So identifying the car as our system, we go ahead and apply our forces, and that's what our free body diagram looks like, with the normal force being at an angle, the force of friction being at an angle, and the force of gravity being straight down. Now in the next example, we have a softball that's being hit. So the softball is actually going to be our system. Now if we look at the forces acting on the softball, obviously we have the force of gravity because we have a gravitational field that's being applied. But the bat that's hitting the ball is actually going to send it that direction. Now if you look at it, you can see that the forces are not going to be balanced. And that's on purpose because in order for this ball to accelerate, it has to have unbalanced forces being applied. So you don't have forces in every direction. And these are going to be the only forces that are being applied to it. F1 is the force of the bat applied to the ball, and then force of gravity pulling down. So the softball is our system, and then we apply our forces to it, and that's what our free body diagram is going to look like for the ball. The next one is going to be a stationary book on an incline. So we're talking about this book that's sitting there, not sliding or anything, and person holding the incline up. So we make the book our system. If we look at the forces that are applied to it, again, we have gravity pulling down, but we also have normal force. Now, just like the car was on an incline, so that means that the incline changes the direction of the normal force. The normal force is not straight up, it's going to be perpendicular to the surface. And again, since the incline is at an angle, then that means the normal force is going to be an angle from what we usually think of a direction of normal force. Then we've got force of friction again up the ramp because it wants to slide down the ramp, but since it's not sliding, the board is pushing up on the with a force of friction on the book. So the book becomes our system, and then we have our forces being applied, and then that is what our free body diagram is going to look like for our book. So altogether, we have these 4 scenarios that show us free body diagrams. One with the dog being walked, one with the stationary car on an incline, and the softball that's being hit, and then the stationary book that's also on an incline. All right, so let's suppose we got several systems here. We're gonna talk about equilibrium forces. Equilibrium forces are forces that put the system in equilibrium, essentially where the net force is going to be equal to 0. So when we have a net force, then we're going to have a force that's in the opposite direction, and it's equal in magnitude. That way, when we add it to the original force, it's going to be 0. So you see the first one, we have 10 newtons to the left, 10 newtons to the left. So in order to balance this out, we're going to have 10 newtons to the right, or 10 newtons east. The second example here, you see that you have 10 newtons and 5 newtons both upward. So in order to balance those out, you need a total of 15 downward, or 15 south. The third free body diagram, you see you have 5 that are going west and 10 that's going east. So these are already opposing each other. So that means the 5 taken from the 10 gives me a total of 5 that's going to be to the east. So I need another 5 west in order to balance that out. Now we look at the last one here. You see that you have 10 newtons to the west and 5 newtons south, which means in order to balance this out, we're going to have 10 newtons east and 5 newtons north. Now, these are two separate forces. What I want to do is I want to apply just one force that takes these two into account, and that's going to be up at an angle. You see, if you make a right triangle out of these, you got your 10 newtons here and your 5 newtons, then the right triangle is going to give us a hypotenuse, and that hypotenuse is going to be our one force. And you can see that's going to be 10 squared plus 5 squared, and then square root that, you get a total of 11.2 newtons. And then you figure out that angle by using opposite over adjacent. Remember, this side was 5 over here and 10 down here, so 5 over 10, inverse tangent, that gives us our 26.6 degree angle. All right, so let's suppose we have a local grocery store that wants to hang a sign with a horizontal pole and a static wire making a 40-degree angle with the pole. All right, so now looking at this system, we have a mass of, the sign has 150 kilograms of mass, and the pole is pushing away to the right away from the wall with a force of 1752. All right, so we know how much force the pole is pushing away. So if we look at the forces that are acting on this, we got a downward force of gravity. We have that pole that's pushing away, but we also have the static wire that's pulling up and to the left. All right, so these are the three forces that are acting. We know it's in equilibrium because we don't want this sign to accelerate. So that means the net force in any direction is going to be equal to 0. All right, so first of all, let's go ahead and figure out that force of gravity because we have the mass, but we don't have the force of gravity. So the force of gravity is going to be equal to mass times 9.8. So 150 times 9.8 gives me 1,470 newtons. All right, so now I have the force of gravity that's acting down. In the problem, it tells me the force to the right, that force 1, we're going to call that, is 1,752 newtons. So we need to figure out this force 2 that is up and to the left. Okay, so just looking at the free body diagram, I've got these three forces acting here. Now what's interesting is this force 2 is up at an angle. It is up and to the left. Now this force that's up and to the left is actually going to have what we call components. It's going to have parts of the force. One part is horizontal, the other part is vertical. Now what's interesting about this is this horizontal part is pushing against this force 1. So the static wire is pulling to the left while that pole is pulling to the right. And then force of gravity is pulling down, and then this static wire is pulling up. So it has this horizontal and vertical forces that are pulling against these other two forces. So let's figure out what these components of these forces are by using Newton's second law, where net force is going to be equal to mass times acceleration. Now notice I have the net force in the horizontal direction and the net force in the vertical direction because both directions are going to have a net force of 0. So for the horizontal direction, we're going to look at the horizontal part, the horizontal component of force 2. That's going to be in the negative x direction, while force 1 is going to be in the positive x direction. So force 1 minus that x component, that x part of force 2, is going to be equal to 0. And in the y direction, the vertical direction, force 2 in the y direction is going to be in the positive because it's up, and then we got force of gravity down, so it's negative. So force 2 in the y, that y component minus force of gravity is going to be equal to 0. So when you isolate each of these components, the force 2 in the x direction is going to be equal to force 1 because there's no acceleration in the horizontal direction. And then the y component of force 2 is going to be equal to the force of gravity because there's no acceleration in the y direction either. All right, now we know force 1 and we know the force of gravity, so that means we know each part of this triangle right here. We know that force 2 is going to be equal to 1752 because it's balancing force 1, and force 2 in the y direction is going to be equal to 1470 because it's balancing the y direction. So what we can do is we can look at this and we notice that this makes a right triangle where the force 2, the vector itself, is the hypotenuse. So we can use Pythagorean theorem in order to figure out what the magnitude or the amount of force 2 is going to be here. So we take that 1470 squared plus 1752 squared is going to be equal to that hypotenuse force 2 squared. So then if we square root both sides, we get 1470 squared plus 1752 squared, and we square root that, and we get force 2 is going to be equal to 2287. So that gives us our force that's being applied in the for up and to the left for this force right here. So our next example here, we have Joe that's wishing to hang a sign that weighs 750 newtons so that cable A, which is attached to the store over here, makes a 30-degree angle with the wall. Cable B is on the horizontal, and it's attached to the adjoining building with a tension of 430 newtons. So that's this cable over here. And then what's the tension in cable A? All right, so looking at this from this point right here where the sign is attached to these two cables, we got one cable that's pulling directly to the right, one cable that's pulling up and to the left, and then we got the force of gravity that's pulling downward. All right, so making our free body diagram, these are our three forces that are acting here. Now, if you look at this 30-degree angle right here with that vertical wall is going to be the same as this angle right here with that vector with that vertical axis. So if you think of the y-axis being right here, then opposite interior angles is what gives me that 30 degrees. Okay, so our three forces, we got F of A pulling up and to the right. I'm sorry, up and to the left. And we got force of B, which is pulling to the right, and then we got force of gravity downward. Now we identify each of these forces. Now in the problem, it tells us that the force of gravity, it actually says that the weight is 750 newtons. So ordinarily we would be given the mass and we'd have to multiply that mass by 9.8 to get the force of gravity. But in this example, we have the force of gravity because it says it weighs 750 newtons. It also tells us this force to the right, this force B, is 433 newtons. So we know these parts right here. Okay, so this vector right here, this force A, is going to have a vertical component and a horizontal component. The vertical component is going to balance the force of gravity, and then the horizontal component is going to balance that force in the B direction. All right, so just kind of walk through this. We have net force equals mass times acceleration. The acceleration is 0 horizontally and vertically. So the net force in the x direction is going to be 0. The net force in the y direction is going to be 0. If you look at the forces in the x direction, we have the horizontal component with the FA in the x direction is going to be equal to FB. And then FA in the y direction, this component right here, is going to be equal to the force of gravity. So these two sides, this one's going to be equal to the force B, and this one's going to be equal to the force of gravity. So I know what each side of those of that triangle is. So now I can use the Pythagorean theorem to figure out that this side, which is going to be the 750, and this side over here, which is going to be the 433, I can do 433 squared equals 750 squared. That's going to be equal to the hypotenuse, which is F of A, and then that's going to be squared. So we square root both sides, and we get that force A is going to be equal to 866 newtons. So that's going to be our equilibrium force for these other two forces.